Welcome. This is the fourth Compton Lecture in this series. So I hope everything went well with the other two guest lecturers. You had Tim Linden in the second week, who was talking about his very exciting research, searching for dark matter. And then in the third week, we had Douglas Watson, who was telling you how we make galaxies in a computer, so how we do those simulations of galaxy formation. So today I want to go a little bit back and go over some of the stuff that Tim discussed. So really going back and looking at what is dark matter. Okay, so this is the first in a series of 3 lectures on mapping this dark sector. So really the huge component of the universe that we don't know anything about. Okay, and dark matter is the one big thing that we don't know about. Dark energy is the other big thing. And I'll be talking about dark energy in lectures, the 2 lectures following this one. Okay, so just to recap what I went over with you in the very first lecture, or anyone who wasn't in that lecture, what we covered was the kind of history of our understanding of the expansion of the universe. Okay, evidence for why we came to this conclusion that the universe was expanding based on Hubble's observations of galaxies at different distances from us. And their velocity at different distances was actually increasing, showing that these galaxies were moving faster and faster away from us the further and further away the galaxy is. So if you take that idea of an expanding universe and you run the clock backwards, then what you get is this idea that all the galaxies which are now moving away from one another actually get closer and closer together, and we roll this clock backwards all the way, and we end up with this singularity, which we refer to as the Big Bang. Okay? So this is what we believe the universe started in. And then we have this interesting phenomena where we're able to make observations using the wavelength of light. Okay? So light has an energy associated with it. It also has something called the wavelength, the length of the light. And because it's moving through space, this wavelength gets stretched into different frequencies, and we call this the redshifting of light. Okay, so in measuring this redshift of the light, we're able to determine the distances of different objects to us. Okay, so we're left with this picture of this unknown moment called the Big Bang, which we really don't know what happened at the moment of the Big Bang. It's a singularity, which means our equations just break down at that moment and they're no longer valid. And then we know that after the Big Bang, there was a period called inflation, where there was a rapid, very, very rapid expansion. Okay? And you have at this very early time this kind of quark soup. Okay? So it's very hot, dense plasma of material and radiation all mixed up together, sloshing around, okay? Causing oscillations in the joint fluid between the particles that we know about, the quarks, and the light particles, the photons. And then because of the expansion of space, everything started to cool down. Okay, the soup started to get quite cold. Particles started to recombine and form heavier elements. And then the light particles no longer were trapped in the soup. Okay, and they were just allowed to stream out freely. And this is the moment of the creation of the cosmic microwave background. So we discussed this in lecture 1 as well. So this happened at about 300,000 years. This is how old the universe was when this light was released, and now has been moving fairly undisrupted through the universe until we're able to measure it today in satellites like the WMAP satellite and the Planck satellite. So I showed you results from both of those experiments in the first lecture, if you remember. So in this picture, we have all the luminous material that we're used to seeing, like galaxies and stars and gas. But we also have very strong evidence for a dominant component of the matter called dark matter, and that's what I'm going to be talking about today. Okay, so this is the unsettling picture that we have for the composition of the universe. The stuff that we do recognize, the heavy elements, maybe neutrinos, I'll talk a little bit about that today. The stars, the gas, the large gas clouds of hydrogen and helium that we see, these only make up a very, very small portion of what we know as the universe. And then this disturbing unknown component called dark matter represents approximately 25%. The dark energy, I'll talk about in subsequent 2 lectures, is an even more mysterious component. Okay? We really are more baffled by dark energy than we are by dark matter. At least for dark matter, we're fairly confident we're looking at a particle, that we have various methods we can use to detect it. with dark energy, we really are in the dark with this unknown component. Okay, so today I'm really going to focus on what is the cosmic evidence for dark matter. Why should you believe us at all? The 25% of the universe is just this unknown component with a big question mark in it. Okay? And so we really do have lots of cosmic evidence which relies on different physics that all point towards the same amount of an unknown material with the same kind of properties. And I'm going to go through each one of these today. So the first will be actually, historically, how we figured out that something was missing. Okay, so just looking at the motion of astronomical objects, from stars and galaxies to galaxies actually interacting with one another in clusters of galaxies, and then looking at very, very large scales, how galaxies are moving in relation to one another. So we call these bulk flows in the universe. Okay? And you can think of these as very large tides in the universe that the galaxies are just being moved around on. Okay? And it's the dark matter which is actually driving these tides. The second evidence is how mass affects the light from distant galaxies. Okay? This is a very different physical effect to the first effect here. So very different physics involved in this. And this is a very, very powerful probe of the matter in the universe, okay? How light is responding to mass and how the mass is distributed. So if mass is clumped or if it's very smooth and evenly distributed, light will respond differently to those two scenarios. And we call this effect gravitational lensing. The third evidence we have is measurements of the clusterings of galaxies. So we can do very simple things like simply counting the number of the clusters, counting the distance between clusters and how they're distributed. Are they all equally distant from one another? I mean, can you not distinguish them? Or are they certain clumps together, certain characteristic distances that you will find galaxies at from one another? Okay. And just that simple counting experiment tells us about the matter in the universe. The fourth evidence is galaxy formation itself. So if we really want to, as Doug was talking about, if we want to be able to write a computer program that generates a galaxy, right? You want to be able to hit return on your keyboard and say, give me back a realistic looking galaxy. It's impossible to do that as far as we know without dark matter. Okay? People have tried, but they have failed. So in order to get realistic looking galaxy formation, we really need this dark matter component in the universe. And the fifth line of evidence is the cosmic microwave background itself. So this radiation released in the early universe bears imprints of the dark matter from that time. Okay, so even though the dark matter was dark, it still affects the light at very early redshifts. So this is the very earliest light that we know about, and this still bears those oscillation signatures of that very hot, dense soup sloshing around. Okay, so the first line of cosmic evidence. So I think it was 1933 when the Swiss observer Fritz Zwicky was trying to measure the mass of the Coma cluster. So a cluster is not just one galaxy, but several galaxies. In the Coma cluster, there's about 1,000 galaxies, which are gravitationally bound to one another. So they're interacting through gravity. And he was trying to measure the mass of this cluster by two different methods. One was actually using a mass-to-light correspondence or ratio. So the amount of light that you see coming from the galaxy should correspond to the mass that is there, right? So if you count up the number of stars that you see and you compare it with the light that's output from our sun, you should have some indication of the mass that is there based on the light. And we call these the mass-to-light ratios. The second approach he was taking in order to discover the mass of the galaxy cluster was measuring the velocities of the galaxies using their redshifts, so using this stretching of the light. And he was also using this in relation to the virial theorem. So with the virial theorem, you relate the actual velocities of the galaxies to the mass that is there. So that's just a mathematical equation he was using, saying I measure these velocities. What is the mass that is there based on these measurements of the velocities? And then he was comparing that with the mass that he found based just on the luminosity. And he found a discrepancy of huge order of magnitude, so a difference of 400 in the two estimates of the mass that should be there based on the velocities and the mass that he saw based on the luminosities. Okay, so this is one line of evidence for this dark material or dark matter, and this is why he called it dunkel material, so dark matter. So this was not enough in 1933 to convince astronomers that dark matter was really there. Okay? I mean, this was just the first hint, but it was really until we had better redshift information. So actually getting the redshifts of these objects from spectroscopy. In the 1970s, it was a team led by an American astronomer, Vera Rubin, where she was actually looking and measuring the velocities of stars in individual galaxies. And not just looking at the rotational velocities of these stars, but actually looking at things like how far the star, so the maximum vertical height that the star goes away from the disk of the galaxy. Because these things are indicative of the actual gravity that is pulling the star back in. So this is, you could think about it like kids on a Ferris wheel or a merry-go-round. The kids have to hold on in order not to be flung off the ride. Okay? So gravity is that force that holds everything together, because otherwise that rotational velocity would just fling all the stars apart. And so we know that there's this very simple relationship between the velocity, the mass of the object, and the radius of the object. Okay? And g here is just Newton's gravitational constant. So you can just think of that as a single number. Okay? So if we know what the mass, or we think we know what the mass of the object is, a galaxy in this case, and we know what the radius of the galaxy is, we can actually see how big this galaxy is, we can measure the velocities, we can check the consistency of this equation, which describes our understanding of gravity in that galaxy. And you can imagine, if we know what the mass is, as we go further and further out in radius, so imagine you're well beyond the radius now of the actual galaxy, we would expect these velocities to go towards zero, to die away, right? Because there's no more material there. This number here, r, is getting really, really big. 1 over a really big number is a small number. So you can imagine we would expect that the velocities should just die off. Okay? This is if our measurement of m is based on the luminous material which is there. But what they actually found was something very different. So this plot is basically showing this mathematical equation here. So on the y-axis, what is plotted is the velocity, which is measured in kilometers per second, and then the radius from the actual galaxy. So as we go further away, this is the curve that you would expect based on the luminous material that you see. Okay, so the luminous material tells you how much mass is there. You measure your velocities, and you would expect this relationship. As you go further and further away, the velocities just die down. But what they actually measured was this green curve. Okay? Showing not only do the velocities not die away, but they level off, and there is a slight increase in the velocities as you go further away. So this is showing that as you go further away from the galaxy, there's more material here which is keeping these objects on the outside gravitationally bound. Okay, there has to be more material there in order to give this relationship. And what is the stuff that's out here? I mean, you might say to yourself, well, this is the edge of the galaxy, right? Where we see all the stars. But actually further out there are more stars. I mean, they're fewer. But also the very big important thing as you move further away is that there are large gas clouds. And these gas clouds are what allow us to measure this rotational velocity out to much greater distances. So this really was a very strong evidence for there being more material in galaxies. So you can imagine, for galaxies, this scale is a kiloparsec. So 1 parsec is about 3.2 light years. So that's the time it takes light to travel. So this is really large scale, right? So this is the scale of galaxies, the kiloparsec scale. But we do have evidence from other scales. So if we look further and further out. So now we're not just looking at individual galaxies and looking at the dark matter that surrounds them. We're looking at these clusters of galaxies. And this is a really beautiful map that was made by the 2-mass redshift survey of our local environment. So these are all the clusters of galaxies that are surrounding ours. Okay? So this is the Milky Way center here. The Virgo cluster is the one that's the closest to us that we're a part of, which is up here. And you can see that there's several other clusters. This is the Coma cluster, the one that Fritz Zwicky made the measurements of, the Booty supercluster. So many of these you might recognize the name of. The Abel cluster over here. I'm trying to think. Okay, so I have some pictures later in the talk of the clusters, but they're not actually mentioned here. So as you can see, our environment is very, very busy, and there's lots of places where we can make these measurements of the dark matter in different clusters on different scales. So one of the interesting things we can look at is when we have this map of the clusters and galaxies in the clusters, we can also look at, well, what are the velocities of these clusters? How are things moving on really large scales? Okay? We know that the universe is expanding, but in addition to this expansion, objects are being pulled away from one another and towards one another because of the force of gravity. Okay? And these additional velocities will tell us about the matter in the universe on these really, really large scales. So this is called the bulk flow on really large scales. So this is actual data showing the shaded regions are overdense regions. Okay, so these would represent clusters of galaxies. The kind of pale white regions, these are underdense regions called voids, where there's not much happening, maybe one or two galaxies, but not much. And then the arrows on this map represent the velocities, the velocity field over this space. And you can clearly see there's this kind of flow, right? And the flow is going out of the underdense regions into the overdense regions. Okay? And this bulk flow tells us about the matter that is there, because the velocities are just due to the matter. And because of these really large-scale measurements of the velocities, these tides, if you like, on very large scales, we end up with measurements of the mass-to-light ratio, so just measuring the mass from the velocities and the light emitted from the luminous material, we end up with these large number of differences of 200 to 300. Right? So this is telling you the difference between the dark mass, which is there, and the light mass that you see. Okay, so this is further evidence on a very different scale that there is dark matter there. So there's a recent project called the Cosmic Flows project, which is a really beautiful diagram. So I'd encourage anyone who's interested to see more of these pictures to go online to this website. There's a movie there if you're interested. It's about a 20-minute long movie showing how they made these maps and how they actually calculated the velocity fields. And I really encourage you to watch this movie. It's really great. So this is just our local environment. They point out the Milky Way here, and you can really see these bulk flows due to overdensities. Okay? They try to represent these overdensities like dips here in our local environment, and these blue regions as these underdense regions. So there really is this tidal flow that we're a part of, and it's matter which is driving these flows of the galaxies. So if we piece all this information together, just looking at the velocities of objects and the mass that we infer from those velocities, and compare it with the light that we measure and the mass to light relationship, we end up with this type of diagram. So very different scales. So 1 kiloparsec is 1,000 parsecs. And remember I said 1 parsec is 3.2 light years. So this you might think is a very large scale. This is the scale we represent, or we associate with galaxies. As we go further out, we represent megaparsecs with clusters of galaxies. And on even larger scales than that, we have superclusters. Okay? And on each of these different scales, we're able to make this measurement of the velocities and the light that we see. And each of these scales is telling us the same thing, that there is more matter there than what we see. Okay? And each of these measurements are actually agreeing with one another in terms of the amount of matter that is missing from our calculations. And we call this the mass-to-light ratio. Okay, so moving on to cosmic evidence number 2. So this is a very important probe of cosmology, and it's very different types of physics from the first type of physics I was talking about. So the first type was based on measuring the velocities of galaxies and the light emitted, just the luminosity of the objects that we see. This second probe is more kind of fundamental in a sense, in that it's based on our theory of general relativity. So as we look at objects like galaxies and hydrogen clouds and things like this, what we're actually measuring is the light emitted from those objects. And that light has traveled a certain distance through space to reach us. Okay? And the kind of cartoon picture of space is this grid which has been distorted. Okay? So you can imagine just a flat rubber sheet. And if the light is traveling across that, or a particle, you roll a ball across that rubber sheet, it will just roll in a straight line. But if you were to place a very heavy object, so imagine placing a bowling ball on this rubber ball, it deforms the sheet downwards. And now if you were to roll that pebble along that rubber sheet, that pebble would no longer just roll in a straight line. Okay? It may, depending on how fast you threw the pebble, it may actually circle around the cannonball and just go down. So this is our cartoon picture, which is just an analogy of what we think is happening in space-time. So general relativity tells us that mass deforms the metric of space-time, and you get these deformations around hot, heavy objects like our sun and galaxies, and that light actually responds to this deformation of space. So you may have always heard light travels in straight lines, light travels in straight lines, but that's not actually true, okay? What light wants to do is light wants to minimize its time of flight. It doesn't care about traveling in straight lines. What it wants to do is it wants to take the shortest distance in time, not the shortest distance, which is a straight line in many people's minds. So you may be familiar with what a straight line is on an actual sphere. So if you think about how planes travel from the US over to Europe, for example, they don't travel in straight lines. Okay? They travel in these great circles. Okay? And that's because when you're on a curved surface, the shortest distance is not actually a straight line. Okay? It may be a curved path. And this is true in curved space-time as well. Okay? Light is traveling on the shortest path that will take it the shortest amount of time, but that is not a straight line. It's actually a curved path. And the amount of curvature depends on how heavy this bowling ball is that you place there. So because we're actually measuring the light coming to us from distant objects, when we measure the curvature of that light, we can actually then deduce how heavy the object is that deformed the space-time. So I just want to show a small movie of this. Hopefully this will work. Okay, so we have a distant object like a galaxy here, and light rays emitted from the galaxy. Now imagine there was a very heavy cluster in between us and this background galaxy. Then these light rays get distorted because of the distortion of space-time. So you can actually see this very faint grid here on the bottom, and this distortion due to a massive cluster. And then from our point of view, what we see is we see these smeared out images around the central cluster. And we also see multiple images. So I'll just show that once more. So we're here, we're seeing this light coming from the distant galaxy. If an intervening cluster is here, it deforms the space-time, distorting the light rays. And as you can imagine, our image of this distant galaxy then is distorted. And the type of distortion depends on the placement of this cluster compared to the background galaxy. You end up with these things like multiple images and smearing out. So this is actually a real image taken by the Hubble Space Telescope of a cluster. And you can see this is a smeared out galaxy here. Right? And this is a distant galaxy, the light of which is being distorted in the cluster in between us and it. So sometimes these gravitational lensings can be really spectacular. And this is like one of my favorite. It's called a horseshoe Einstein ring. So this is an example of strong gravitational lensing. Okay? And there's this cluster in the middle here, and this is a background galaxy which is being completely smeared out and lensed. And the reason this is such a strong effect in this case is the alignment of the cluster with the background galaxy. Okay, so this is quite rare that you get features which are this strong. I mean, if we had these all the time, cosmology would just be amazing to do. We could have unbelievable precision measurements. But the reality is that this chance alignment of the foreground cluster and the background galaxy is quite rare. So what we have to rely on instead is what's called weak gravitational lensing. Okay, so they may be misaligned, and you're also looking at background galaxies which are being lensed by lots of different material along the line of sight between us and that background galaxy. So this is a Hubble satellite image of A bell cluster. I think it's 2218. And you can see in this these orange streaks here. So there's multiple images here of this galaxy which is being lensed. This is also a galaxy being lensed here. So not only do you get a smearing of the background galaxy, you also get multiple images. So why is this important for dark matter? So you can imagine that dark matter, we don't see it. When there's an obvious cluster there and there's lots of luminous light, lots of galaxies, we can say, okay, that's the thing, that's the object that's doing the lensing. But what we actually measure is we measure more lensing than the luminous material that we see, right? So we see more distortion that cannot be accounted for by just the luminous material. And one of the very important things is not just the amount of lensing that the dark matter causes, but the actual distribution of the dark matter causes different lensing effects. So this is a simulation showing luminous material here as the orange kind of blotches. And there are two different distributions of dark matter in these two panels, which give rise to different lensing effects. So in the first panel here, in the simulation, the computer simulation, what we did was we clumped the dark matter around the luminous material. And then we looked at what is the subsequent lensing that you see. And in the second panel, what we did was we evenly distributed the dark matter, okay, so made it not so clumpy. And then you look at the gravitational lensing. So you can see there is a clear difference in this lensing pattern based on the distribution of dark matter. So it's not just the amount of dark matter that we can measure with lensing, but we can also measure how it is distributed in the universe. Okay. So on to cosmic evidence number 3. So when we wanted to understand how galaxies are formed, right? So when we started building these really big surveys and we started making maps of our local environment and even further back in time, we saw a very unique pattern in the cosmos, this cosmic web. And people started formulating ideas for how galaxies form. Okay, how do you get these gas clouds condensing and cooling and suddenly clumping together and igniting and forming stars, but yet remaining gravitationally bound and then forming structures like galaxies? Okay. And within that picture, you even have a more complicated picture of, well, you have different types of galaxies, right? We know that there are these beautiful spiral galaxies that we see all the time with the nice spiral arms, but then we also have elliptical galaxies which look very, very different to spiral galaxies. And in this picture, people started to realize that you needed more material there. You needed this dark matter scaffolding in which you built your galaxy, because otherwise it just would not work. And this really came about because of computer simulations. So in the standard picture now that we all think that happened is this hierarchical galaxy formation. So in this picture, what you have are smaller objects. So this represents maybe a clump of gas, so luminous material that we know about, which resides in a much, much larger dark matter halo. So this halo is just, this is our term for a big clump of dark matter. Okay? And these large clumps of dark matter form gravitational potential wells that luminous material like gas and dust stream into and settle to the bottom of. Okay? So the dark matter scaffolding is very important for forming these wells where all the gas can accumulate, and then star formation and galaxy formation can occur. And then in this picture, what you have are not just galaxies forming in isolation, but you actually get mergers of galaxies. So these two combine, the dark matter halos merge into one, and you end up with more than one galaxy inside one dark matter halo. That's not always the case. Sometimes you will just have one galaxy inside the dark matter halo. But these things all combine and form clusters of galaxies that we see today in maybe one dark matter halo. So this approach is called the bottom-up theory of galaxy formation, where small things combine to form larger objects. And in the computer simulations that we run, so this is an output from a computer simulation which was run in Durham University in the UK. And in green here, this is the dark matter, okay, in our simulation. And you can see a very distinctive pattern here of kind of a cosmic web, right? So long, thin filaments, and then these dark, underdense regions. And they form kind of bridges towards one another. And in this simulation, we also had gas particles and star particles in order to simulate how galaxies form. And the white dots here are different types of galaxies. And there's a very clear prediction for the places where these galaxies will form in the dark matter scaffolding. So what do observations say about these predictions? So if we compare, this is a computer simulation of what we think the dark matter structure looks like. So this is a different simulation now. So the colors are really just up to the theorist. Some people are very particular about the colors they use. So this is still just the dark matter, which is represented here in red and blue. And in this simulation, what they've done is they've zoomed in on a dark matter halo, so this clump of dark matter. And inside this clump of dark matter, what you see are these long tendrils. Okay, so we call these filaments. And these filaments of dark matter are very important for galaxy formation. You can think of these as expressways. They're like expressways feeding into a city center. Okay? And what they actually do is they allow the gas, which form the stars and the galaxies, they allow the gas to flow into the center of the dark matter halo. So one of the things that was interesting is that, I think this is a result from 2014, is this is actually a detection of one of these cosmic filaments. So what this picture here is showing This is the results of this team Cantaloupe. I think this is a joint US-UK team. And what they were doing was they were studying distant quasars. Okay, so a quasar is a very, very luminous object. So you can think about it as a galaxy. So it's actually a very, very light beam of light which is coming towards us. And this quasar is illuminating gas around it. Okay? So it's actually lighting up the region around it. And you can actually see this cyan color here, this light blue filament out here. And even though in this picture it looks very small, this is a huge tendril, a huge filament of cold gas. And it stretches for about 2 million light years across. So this is the largest filament that we have detected to date. And this agrees with our theory of galaxy formation that these long tendrils are actually tracing out the dark matter. Okay, so these are our way of identifying these filaments of dark matter. Another interesting recent detection is a filament between two clusters. So this is by a very different method. This method was using gravitational lensing. So the two clusters are here and here. And these lines are just showing the mass distribution that we infer from gravitational lensing. And what you can clearly see is that there's mass in between the two clusters. And there's a very particular shape to that mass. And this connection between the two clusters is our detection of a filament between the two clusters. And this paper appeared in Nature in 2012. So very, very different detection method for these long tendrils or filaments of dark matter, which our simulations predict. And they're very important for galaxy formation. Okay. Moving on to cosmic evidence number 4. So galaxy clusters are very important because they are the largest gravitationally bound objects in the universe. I mean, you might think, well, galaxies are huge, right? You've got billions of stars in them, they're all gravitationally bound. But galaxies are not the biggest things which are gravitationally bound. You actually have then galaxies in their own right which are bound to one another. And these are the largest things that we know about, these galaxy clusters. And we even have detection of superclusters, which are clusters of clusters. And these objects are gravitationally bound. So this is showing the actual output from the SDSS survey, so the Sloan Digital Skies survey. And this is a map of our local environment. So we're at the center here, and we're looking outwards. And what you can see is these filaments and overdense and underdense regions. And this looks remarkably similar to our cosmological simulations. So this is really showing that we are on the right track, okay, because these are observations. And then if I was to compare that with computer simulations, they would look remarkably similar. So we will actually be talking about that in a later lecture. I'll be going into detail of these cosmological simulations that we do and how we end up with such a convincing picture for structure formation in the universe. But if we were to zoom into just a small region of these observations, we see beautiful things like this, where every point of light is an actual galaxy, which is gravitationally bound. So probably one of the most famous pieces of evidence for dark matter is this so-called bullet cluster. And this was discovered, I think it was 2006. So what you're seeing here is actually a crash. Okay? This is the wreckage of a huge crash. And it's two galaxy clusters, which basically crashed into one another. And because there's a lot of empty space in galaxy clusters, the dark matter, which we consider as a non-reactive material, so we call it collisionless, the dark matter actually just passed straight through and is detected on either side of this cluster. So this image is a composite image from different telescopes. Okay? Different methods went into making the measurements for this one image. What you have are measurements of the hot X-ray emitting gas, which were taken with the Chandra X-ray Observatory here in the middle, which is shown in red. And then you have observations of lensing from the Hubble Space Telescope. So lensing shows us that the mass distribution is actually either side. So all the luminous material that we see is in the middle, but if we were to look at the gravitational lensing of background galaxies, the lensing tells us that most of the mass is sitting either side of the hot X-ray gas. And this hot X-ray gas is a real footprint, a real signature of a collision between two clusters. So when galaxies collide, you get the hot gas and dust actually shock heating. As it collides, it's a very, very turbulent interaction. And then the output is very high energetic photons, X-ray photons. So this is a computer simulation of how we think the bullet cluster was formed. So these are the two clusters with their dark matter halos shown in blue, luminous material shown in red. And you can see that as the two merge and combine, the X-ray material shocks and stays in the middle, it stalls, because the luminous material is not only interacting gravitationally, but there's also an electrostatic interaction, okay? Because there's other forces at work there which are causing the luminous material to clump in the middle. But the dark matter only interacts gravitationally, okay? So it does not interact with light. So there are no electrostatic forces which cause the dark matter to stall in the middle. So that's why we consider this dark matter to be fairly unreactive. Okay? The only interaction it takes part in is the gravitational interaction. So we have other beautiful images of clusters out there which show similar misalignment between the luminous material and the dark matter. So this is another example here, Abell 520, where you can see the stars are actually been displaced either side of the subsequent merger. So this is again a merger of two clusters. And then in the middle, we can infer the dark matter material from gravitational lensing, and the hot gas is actually stalled in the middle here too. So this object, the actual misalignment of stars and dark matter here, is quite unusual. Okay, so on to cosmic evidence number 3. So by the end of this, I hope you're going to be totally convinced there's dark matter. Okay, so this is, sorry, the numbering's gone wrong here, so this should be cosmic evidence number 5, I think. So this is really another very compelling pillar of why we think dark matter is out there. And this is information coming to us from the very early universe. So anyone who wasn't in lecture 1, we chatted about how after the Big Bang you had this primordial soup of material where light particles, the photons, and the material were bound to one another. Okay, and we're just sloshing around. A very hot, very dense environment. And then because the universe expanded and cooled, the material itself also cooled. And you get the very primitive particles, the quarks, combining to form elementary particles like protons and neutrons. And then you get the light particles, the photons are just able to free stream. They're no longer bouncing off these protons and neutrons. And this is actually the light from that early time. So if you remember, these hot and cold spots, these blue and red regions here, are just telling us about different temperatures over different regions of the sky at that very early time. So if you remember, we spoke about music in the early universe because we said this primordial plasma was actually oscillating. And oscillating, you can compare it with oscillations in sound waves. And the same way that people decompose oscillations in sound waves, so if you pluck a guitar string, there's a fundamental mode, right? If you just pluck it without putting your fingers down, that's a fundamental mode of oscillation for that string. Once you start putting your fingers down and you pluck that string again, you get different modes, so different oscillations in the string. Okay? And these fundamental oscillations are related to properties of the string, the length of the string. And we can also use this analogy to understand these oscillations in the primordial plasma. Okay, so there's different oscillations on different scales, and we can look at the size of those different oscillations. So this movie here, I just want to say that the actual oscillations are caused by this interplay between the photon and electron pressure. Okay, so in this soup, gravity wants to pull everything together into deep potential wells, but then electron pressure is repelling that. Okay, so this gives rise to this oscillation. So in this movie here, in the left-hand panel, what you'll see are the different hot and cold spots. Okay, so this is just showing you the size of these oscillation regions. And over here, what is shown is a graph of the difference in the temperature on different scales. Okay, so this red bar will move along, and this picture here will change. So it's just showing you the different modes of oscillation. So what we see in this plot is on very, very large scales, the differences are quite large, right? The hot and cold spots are very large. And then as this moves along, the very large peak here corresponds to about an angular degree in scale. And these are the most common hot and cold spot sizes that we see. And the amount of physics that goes into understanding why this is, why we have these hot and cold spots of different sizes, tells us about this plasma in the very early universe. It tells us about the gravitational interaction and the electron pressure between the material that was there and the photons. So this is telling us about the amount of dark matter that was there, okay? Because it's the gravity which is very, very important for these oscillations. So one thing we can look at is, okay, so we have this complicated graph of the actual oscillations on different scales, the size of these hot and cold spots on different scales. And in our heads, we should be thinking, okay, well, these are due to gravity and electron pressure sloshing back and forth, causing different oscillations in the fluid. And all we're doing is we're counting the number of these oscillations, the size of these oscillations at different scales. And we know that the amount of material, the amount of matter there, is what is causing the gravity. And so if we were to change the amount of matter, then this graph should change. Okay. And this plot is just showing, if we were to change the amount of matter here, so just think of these numbers as the fraction of matter in the universe, then this graph changes dramatically. So this is our theoretical prediction for what the number of oscillations of different size in the cosmic microwave background should look like if we change the amount of material. And what we actually think, in order to match the observations, if I can stop this maybe just in time, oh no. If you look at when it gets to about 0.25, this is the only oscillation scale, the only signature which compares, which agrees with our measurements. So all the other values for the amount of matter in the universe do not agree. So it's the fact that we're able to measure the cosmic microwave background with such extreme precision, which is another clue to the amount of dark matter. And it's not just telling us roughly what the amount of dark matter is, it's telling us it with a huge amount of precision. And then if you go back and you think about all those other lines of evidence for dark matter, that number that we get out from the microwave background agrees with the number we find from the rotation of galaxies, the bulk flows on really large scales. It also agrees with the amount that we infer from gravitational lensing. So all these things are just, it's not a huge coincidence, okay? We have to face the fact that dark matter is out there, and all the different observations are telling us that it's 25% of our universe. So these are just showing us the precision that we're able to measure this spectrum. So these red points are data points from the Planck satellite survey. And these are really exquisite measurements. And then in green, the green solid line here, are our theory. And as you saw from the previous movie, any other value for that dark matter component would be wildly discrepant with these measurements. Okay, so we need to still, ask ourselves questions of, can't we just fiddle these observations by maybe modifying our theory of gravity? Do we really have to turn to an unknown component and just say, oh, well, it's another particle, and we don't know? Maybe our theory of gravity is wrong. Maybe we need to do some alterations there. And people have looked at this, okay? So the interesting thing is you can fit galactic rotation curve observations by modifying gravity slightly. Okay, so these small-scale observations of how galaxies or how stars are rotating around galaxies, you can fit those observations by modifying gravity. Okay, but all the other observations, you cannot do that consistently. Okay, and there are theorists out there who are still trying to do this consistently, but it's really, really, really hard. Okay, and so when the explanation faces you of maybe it's another particle, and all the observations can be fit with that, a consistent story of a particle which fits all these observations, then the community is starting to face the fact that, yes, it is another particle, another component of matter, which we need, rather than modifying our theory of gravity. So this plot here is showing an example of how badly the theory of modified gravity does to explain dark matter observations. Okay, so this is a bit of a complicated plot, but we'll just take it slowly. So the y-axis here is just basically measuring how matter clumps. Okay, so all you're doing is just going out there and looking at the distance of galaxies to one another, and you're just counting the number of galaxies at different distances. Okay, so this x-axis is just the distance between the galaxies. And this is actually a 1/length scale here. So very, very simple. All you do is just take something like the Sloan Digital Sky Survey, the data points from that, all the positions of all the galaxies that you see, and then basically just count how many pairs you see at different distances from one another. And the results of that data is shown as the red data points here. Our theory, which includes cold dark matter, is shown as the solid black line. So you can see it fits the theory really well. If you don't have any dark matter, okay, if you just have the luminous material that we see, then you get this blue dashed line here. So this is wildly discrepant with the observations. If we were to use that modified gravity theory, which some people still work on, you would get these solid blue lines here. And the reason you see these massive bumps here are actually the same oscillations that you get in the cosmic microwave background. Okay? So this is just an imprint of oscillations in the clumping of material. So the take-home message from this is it's really hard to fit these observations without dark matter. Okay? People have tried. Okay. So we have to face the fact that lots of evidence points towards a really strange universe. We may not be happy with it, but what can we do? 25% dark matter, 23%. So our standard model of cosmology, the name for it we give is lambda CDM. So the lambda part here is referring to the dark energy, which I'll talk about in lectures 6 and 7. And the CDM part stands for cold dark matter. Okay. So you have to keep in mind, in the standard model, okay, so this is our theory for how stuff in the universe formed and how it interacts with one another, that dark energy is not the same as dark matter. Okay? We really do think dark matter is a particle. So there's this cool website you can go to called Particle Zoo, where if you have a favorite fundamental particle, you can buy a soft toy that looks like that. So this is what people think the dark matter is. Okay. So let's walk through why the cold and the dark before the matter term. So the dark is basically referring to the fact that it does not interact with light. So the reason we're able to see any stuff in the universe is because light particles bounce off that object or are emitted from that object and then travel into our telescopes or into our eye. So basically, the dark matter doesn't interact with light. So the photons just basically don't react with the dark matter, and we end up with this very simple picture of this is what dark matter is, and then not dark matter is anything that emits light. So in fact, this is not so strange. We have already found some dark matter. Okay, so if you guys have heard about it, these neutrino particles are dark matter, and we routinely detect these particles. So a little bit of background on neutrinos. Neutrinos are weakly interacting neutral particles. So neutral in the sense that they do not have a charge. Weakly interacting refers to the fact that we have fundamental forces in our universe. Gravity is one example. The weak force is another example of a fundamental force. So this force is involved in the radioactive decay of particles. And neutrinos are produced in the radioactive decay of particles. So for example, the decay of the neutron involves the neutrino. And we used to think that these particles were massless. But neutrinos have a very, very interesting property, which is they have a bit of an identity crisis. If they're produced in a certain state, so we now know that there are three what are called flavors of neutrinos. We call them the electron neutrino, the mu neutrino, and the tau neutrino. These are three fundamental particles. All three are neutrinos. All three are associated with different radioactive decays. What we know is that if a neutrino is produced in a certain flavor, in one of these three states, and it travels a certain distance, there's a non-zero probability for it to change and oscillate into one of these other three states. And this is a really profound quantum mechanical process that we do understand very, very well. And we see it happen all the time. So neutrinos are produced in the sun. They're traveling towards us, millions of them. And they're actually produced in this flavor state, the electron neutrino. And then when they get to Earth, we actually detect a certain proportion of the other two, the mu and the tau neutrinos. So we know that they have actually oscillated on the way to us. And neutrinos have a small mass, okay? It's very, very small. So we used to think they were massless. We used to think they were like photons, like the light particles, that were massless. And your mass also determines how fast you travel. So light particles are massless. They travel at the speed of light. We used to think neutrinos travel at the speed of light as well. We now know that they do travel very, very fast, but not quite at the speed of light because they have a mass, but a very tiny mass. So they do travel very, very fast, nearly relativistic particles. And their mass is very small, 1/1,000,000th the mass of the proton. So these particles are very, very interesting. There's lots of cutting-edge research going on to understand more about these particles, but we do understand a good bit about them already. And we routinely detect them on Earth. They're produced, for example, in the sun, and they travel to us. Neutrinos are very weakly interacting, okay, so they're pretty boring. They really don't like to interact with stuff. And this is what makes them a good dark matter candidate. Because when they're produced at the center of our sun, they basically just shoot straight out and head towards us. Whereas something like the photon bounces around inside all the material in the sun, and there is a time lag between the photons from the sun and the neutrinos from the sun. These neutrinos are also produced in things like supernovae, so massive explosions of stars, of old stars near the end of their life. We also routinely produce neutrinos in things like nuclear detectors. Okay? So one of the places which has the most nuclear detectors is Japan. And this is why historically a lot of the neutrino detectors were built in Japan. So this is showing a picture of the neutrino detector called Super Kamiokande in Japan. This is a small boat here with people inside floating on water. So this is a very, very large detector filled with water. There is another detector at the South Pole called the Ice Cube Telescope, which is looking for neutrinos, astrophysical neutrinos. And the medium in this case is not water, like in Super Kamiokande, but is ice. And this is one of the largest, I think this is the largest neutrino telescope on the Earth. So it's a 1 kilometer squared neutrino detector. And their kind of claim to fame recently is this detection of incredibly high energy neutrinos. So if you think about the energy associated with the mass of the proton, we call that a GeV. The energy of these neutrinos that were detected are 10 to the 9 times the energy associated with the mass of the proton. So that's 10 to the 9 is a very, very large number. They detected 2 of these events a while ago. They nicknamed them Bert and Ernie. They since have detected 28 more high energy events. So these are in the PeV range. Okay, so really, really high energy events. We still don't know where these neutrinos are coming from. This is like cutting edge research. But we're pretty certain that they're extragalactic, so they're coming from outside our galaxy. Okay, so on to the next part of the dark matter. So why the cold part? So the cold just refers to the dark matter having a very small velocity dispersion. Okay? And the reason we know that the dark matter needs to have a cold velocity dispersion, the evidence from this came from our computer simulations. So when we tried to form galaxies, we can actually put in different recipes for how the dark matter behaves. We can say, okay, well, what if it does have very large velocities? What if it has very small velocities? And then we can look at the resulting cosmic web, which we get at the end of our computer simulations, and then we can compare it with observations of how galaxies look in our universe. So in the top 2 panels here, this is showing a computer simulation with cold dark matter, so very small velocities. And again, you see this cosmic web-like material with filaments and underdense regions. And this is zooming in on one dark matter halo where a galaxy would ultimately form. If you were to turn up the velocities of the dark matter, so say you had something like a hot dark matter material, you can see that the structure that you get looks very, very different. Okay, so really this is kind of the 3 little bears story of galaxy formation. You could have hot dark matter, warm dark matter, or cold dark matter, but in order to have galaxy formation, the temperature needs to be just right. Okay? And in the top panel here, all of our observations are pointing towards a cold dark matter component. And this is one of the main reasons that neutrinos can't be all the dark matter. We know that they are a dark matter particle, but they can't be all of the dark matter because neutrinos travel very, very fast. Okay? So they're near relativistic speeds on average, and they would end up giving us a universe like this if all the neutrinos were dark matter. And if you remember back to the slide where I showed galaxy formation, where small objects clump together and form larger objects, we call this the bottom-up story of galaxy formation. Hot dark matter gives a top-down theory of galaxy formation, where you get very large structures that form first, and then fragment into smaller structures. And we know that that is not how galaxies form. So neutrinos can't be all of the dark matter. Okay. So you did hear a lot about searching from dark matter from Tim Linden, so I just want to briefly talk about this before wrapping up. So then the question is, well, you know, if you don't have any idea what the dark matter is, how do you look for it? Okay? So it's by a process of elimination. What you do is you say, okay, well, all the stuff I do know about in the universe, all the neutrinos coming from the sun, cosmic rays coming from maybe supernova explosions, I know all of those things, okay? And those are considered background. So what you do is you take your detector and you put it in a mine underground and you shield it from all the things you do know about. And then you hope that if you do detect something, right, some collision inside your detector, then you hope that it's due to a dark matter particle. And then the consistency check is that the mass that you would find in your detector for the dark matter particle agrees with all those other cosmic evidence. Okay, the cosmic evidence for rotation curves, for the cosmic microwave background, for gravitational lensing. So that's a consistency check on these detector experiments. And this really is a very, very exciting active area of research right now. So the hunt really is on to find dark matter. And we have lots of underground detectors. So these, a lot of the time, are in working mines all over the world, where you're trying to shield your detector from background noise. And then you're trying to figure out, well, is there any other particle coming in, hitting off my detector, and causing a recoil energy that I can measure? Other experiments are trying a different approach. So here we're looking at if our galaxy, if the Milky Way is sitting in a dark matter halo, then as we move around in our galaxy, we should be able to detect a kind of wind coming towards us of these dark matter particles. So there are other detectors looking at this. And then what Tim spoke to you about 2 weeks ago was his observations looking at the center of the Milky Way for dark matter annihilation signals. So if dark matter particles collide and actually destroy one another, there should be energy produced in that reaction. And maybe we can detect that coming from the center of our galaxy. Okay, so I'll finish up there. I just want to say next week we have another guest lecturer who's Austin Joyce, who's a postdoc at the KSCP here in Chicago. And he will talk to you about this really exciting recent discovery, which is from the very early universe. So these are primordial gravitational waves in the early universe. So if you haven't read some of these popular articles in the newspapers, I'd recommend you do, maybe before you go to his talk. But if not, he definitely will tell you everything about it. So maybe save your questions about that till you see his talk. So thank you. Are there any questions? Yes.
I gather your simulations are mostly Newtonian practicality.
Yes.
Because the dark matter is only gravitationally interacting, so there has to be something to prevent condensation in black holes. And yet that wouldn't be built into your simulation because it isn't Newtonian.
Sure.
So it works after all, the center of every galaxy has a black hole.
Sure.
It can't be all just stellar generators.
Yeah. So there are different types of simulations. The simulations that I work on, for example, are dark matter only. So in that simulation, I don't have black holes. Okay, so black holes are simulated in other simulations where you do the complicated physics, right? So mostly when you do a simulation which involves black holes, you're just simulating one galaxy, okay? And not everything falls into a black hole. Okay? So there's a cosmic horizon with a black hole, and if you go beyond that event horizon, then you fall in. But objects can happily orbit a black hole without falling in. So it's really about the scale you're interested in simulating. If you're interested in simulating clusters of galaxies, then you don't need to simulate a black hole, because black holes don't affect clusters of galaxies. If you're interested in simulating a galaxy, a single galaxy in detail, then yes, you need to include general relativity, and you need to include a proper description of how your black hole is interacting with the gas in the galaxy. So it really depends on what type of physics you're interested in.
But dark matter has to interact with the black hole.
Yes, but it doesn't have to. So if you are looking, so basically the dark matter could happily orbit around the black hole and not fall in. So we routinely detect the black hole at the center of our galaxy, and we measure the stars just orbiting around the center of our galaxy. They don't fall in. Yeah. So another question?
When you divide the universe up into 4% atoms and 70, what are the actual units that the atoms are, for dark energy is 76%.
Sure.
what kind of things?
Yeah, so it's a fraction. So we have this, we call it critical density. Okay, so there's a critical density associated with the universe, which is a number. Okay, I forget the actual figure now, but it's like a grams per centimeter cube number. It's just a density. And that critical density is related to the expansion of the universe. Okay? And these numbers are fractions of the critical density, so that's why they're dimensionless.
Okay.
Yeah. Yes?
Your slide of the Cantaloupe,
Of what, sorry?
Cantaloupe study
Yeah.
of the tendrils of dark matter,
Yeah.
galactic tendrils. I wondered if you indicated that whether the tendrils facilitated star formation and how, I guess you're saying that dark matter doesn't interact, that it's a kind of a historic, I don't know what you say.
I mean, you can really think about the dark matter as being these roads which facilitate movement of the gas into a potential well. So that analogy of thinking of them like expressways, which material flows into a central region on, is quite.
So they would form star. They would.
So this
the universe is it is what it is. So without it, stars couldn't form.
Exactly. So you really do need these tendrils of dark matter that the fluid flows along, so that the gas flows along, and then falls into a central well. So it's also, I didn't go into the details of it, but it's also the temperature of this gas is important. So the gas flowing along as cold gas and falling into a dark matter potential well is very important for forming stars, because you need the gas temperature to be right as well in order to form stars.
Well, what about at the early stages of the universe? Would dark matter act in the same way for early star formation?
So yes, we think
Is that
so.
the
Yes.
assumption?
Yeah. Exactly.
I see.
Yeah.
Thank you.
Yeah, if dark matter doesn't cool because that's emit photons and all that, how come it is cool now? What mechanism do you theorize that permit the dark matter to cool?
So the dark matter. So I don't quite understand your question.
Well, we say that the dark matter is cold, right?
Yeah. Yeah.
So since dark matter doesn't emit photons,
Yeah.
it doesn't cool up.
Yes.
Regular matter does. They get hot and they emit photons, they get cooler, then they condense and so on.
Sure.
So what is the mechanism that allows the dark matter to cool up? Because when the universe formed, everything was hot, right?
Sure. So it's the actual production mechanism of the dark matter in the very early universe. It depends on the particle the theory you have in mind. So there are many different particle candidates. It's not something I spoke about today, but theorists have different candidates for a dark matter particle. And then in your theory that you write down for a dark matter particle, then you have to explain how it was produced in the early universe. Okay? And it depends on the dark matter particle that you believe in. So it depends on how you think that dark matter particle was produced. But all those things need to be self-consistent. Okay? All we know is we have the observational evidence to tell us it was produced in a cold state, and it is a cold today in terms of having small velocities. Okay? But how you produce it in the early universe, it depends on which particle candidate is your favorite. Okay? Because we don't know what the particle is at the moment. Right? So it's only these observations which will tell us which are true. And I didn't go over the candidates for dark matter, but I think Tim did in his talk. So there are many different candidates for dark matter. So for example, there's a particle physics theory called supersymmetry. Okay, so this is a lot more detail than I wanted to go into. But in that theory, every particle we know about has a supersymmetric partner. And in that theory, there's a dark matter candidate which in the very early universe is produced in a cold state, so with low velocity dispersions. Okay? And the velocity, if you remember, is related to the mass. So light is massless, travels at a very high velocity. So then when you say dark matter is cold, it means it has a small velocity, and then that has implications for its mass. Okay. Sorry, you had a question.
I'm having difficulty understanding how a particle can be massless. How do you have any evidence of something that doesn't have mass?
So, I mean, if you think about it,
Repeat the question.
yes. So the question was, how can a particle be massless? Okay? And I think the important thing to think about is Einstein's theory. Okay? So Einstein told us that energy and mass are equivalent. So if you have energy, it's exactly the same as having mass. So the photon has energy. And it's really the idea of not separating those two in your mind. Okay? So if you have mass, you can convert that mass into energy. Right? So you can take a lump of coal, you can burn that coal and produce heat energy. Right? So it's this idea of not separating the two. Consider energy as equivalent to mass. Yeah. Yes?
The current issue in Scientific American says there's a crisis in physics because supersymmetry has not been confirmed. It doesn't look likely.
Yeah, that's true. Yeah.
Is that a problem for dark matter theory or not?
No, it's not a problem for dark matter theory because there's plenty of other particle candidates which we have, which could be dark matter. It is a problem if you based your career on supersymmetry. But, yeah.
If galaxies are gravitationally bound to dark matter scaffolding, how would you see a wind of dark?
So, can you repeat that question again, please?
You mentioned briefly, just as you were finishing the lecture, about trying to detect the wind of dark matter.
Yeah.
And if we're within a galaxy that's gravitationally bound to a scaffolding of dark matter, how would you see the wind of it? Would it be moving with you?
So basically, because the dark matter is interacting gravitationally with the Earth, there will be an effect on our relative motion compared to the dark matter. So this is this wind that people look at. Yes, back of the room.
Okay, we've been shown, especially like last week, these gravitational lensing formations,
Yeah.
and we see galaxies at a great distance being lensed by something in the foreground.
Yeah.
Now, like that. But they always appear with regular matter, with ordinary matter, which kind of implies that the dark matter has to rely on the ordinary matter to be there, because we don't see them in isolation. There are no lensings where there is no ordinary matter. Or at least I don't think there are.
So the bullet cluster is an example of where there's a very clear separation of the luminous matter and the dark matter.
Well, that's only one, though.
Oh no, we have other observations. The bullet cluster is kind of the poster child for it because it was kind of the first. This is why I showed this other example here. Yeah.
Now, the question becomes then, though, haven't there been experiments for looking at dark matter in our near vicinity here, but they've all come up empty, so to speak? Why would that be?
So it depends on which experiments you're talking about because there are lots, and a lot of the experiments are looking for different things. So, so this is why I didn't go into this in detail because I would have assumed that Tim went into more detail on the actual experiments. A lot of the experiments have found some things, some of the experiments haven't. In terms of actually agreeing with one another, they don't. There are some underground experiments which have detected signals of dark matter particles of a certain mass. And these experiments are yet to agree with one another. Also, the statistical significance of the detections is very, very low. These experiments are incredibly difficult because the main thing you need to understand really well and block out are the noise, right? The background stuff. And to complicate matters, all of these experiments are actually using different detector designs. So it's very hard to compare with one another. So at the moment, there is a lot of argument in this field over who is right, because at the moment there's a lot of clashing. They're not agreeing with one another. Some experiments are finding nothing. Other experiments are finding weak signals of detection. At the moment, there's not enough evidence for anyone to claim a detection. It's still really ongoing cutting-edge research. Yeah.
You pointed out examples here of what's happened when two galaxies collide. And I can recall from several years ago, a lecturer pointed out that two galaxies can collide and pass right through each other with no suns colliding. Is it sometimes they do and sometimes they don't?
So most of the time, so in the collision movie that I showed, those were actually clusters of galaxies. But you're right, when galaxies collide, there's so much empty space that the stars, you don't get stars hitting stars, right? You don't get that. But in galaxies, there's a lot of gas, a lot of just free gas, which is not bound up in stars. And that gas does interact gravitationally. And you get this shock heating of the gas. So the gas gets heated because it gets compressed by the merger. The gas gets heated to very, very high temperatures, and this is why you see this X-ray emission from that hot gas. So the X-ray emission from hot gas is a very clear signal of a merger taking place. But you're right, in terms of stars hitting one another, that doesn't happen. There's a lot of empty space in galaxies. Yeah, at the back.
If neutrinos were created in the Big Bang, were they absorbed in the formation of luminous matter and are now being released in the fusion process?
So neutrinos are released in the fusion process. So in the sun, neutrinos are released regularly. They were produced in the early universe as well. So neutrinos, you really should think about them as particles that are produced in radioactive decays. So for example, when the neutron decays, which has a relatively short half-life, I think it's a few minutes, the neutrino that is produced in that is the anti-neutrino of the electron neutrino. So it's, each neutrino has an anti-particle associated with it, and it's the anti-neutrino which is produced in that. So yes, neutrinos are produced regularly. We do understand them really, really well, but they have some very unusual properties which make them still very interesting objects to study. But they can't be all the dark matter. Any other questions? Yeah.
Photons have a mass.
Photons are massless.
Well, when they're traveling, don't they have some, they're deflected by the sun. Is that the interaction between, is it gravitational interaction?
So because mass and energy are equivalent, they respond the same to the gravitational metric, the deformation of the metric.
So a photon is pure energy and no mass.
Yeah. So because mass and energy are equivalent, the two react the same to the deformation of space-time, and that's what general relativity does.
Follow up on that.
Well, let me finish. There being equivalent doesn't mean that you can transform one into the other.
Yeah, it does. Yeah.
It does.
Yeah.
See, but you can't transform. You can transform photon energy into mass.
So in a sense, we haven't detected that. So you can have a photon being absorbed by an object. So for example, what you can do is a photon could be absorbed by an object which has maybe an electron in it. That energy excites the electron, and then we may see this object which has the electron, maybe a nucleus or something, or some atom, that increases in temperature. And then that increases not the rest mass of the object, but just the measured mass of the object. So this transferal of energy, which may be then detected as mass, is possible.
Okay, what I was attempting to drive at is we generally think of detecting light as impinging, hitting us directly.
Yeah.
But if it's passing by perpendicular to our line of sight, does it have an effect, a gravitational effect? And if a sufficient number of photons pass by, would we detect it gravitationally?
So it would, but it'd be absolutely tiny. So for example, like because I have mass, I am deflecting light right now. But there's no way you would ever detect it because it's absolutely tiny. So anything that has a mass or equivalently in energy causes this gravitational detection, but it's so minuscule, so tiny, that we would never be able to detect it.
And given all the photons, free photons in the universe, like the cosmic background radiation, that is not sufficient to account for any dark matter.
No, I mean it's completely swamped by astrophysical masses in terms of their gravitational density. Absolutely swamped. So one last question?
Responding to that slide of the race is on to find dark matter.
Yeah.
Is there anything else coming? Any big machines? Any huge observatories that you haven't mentioned yet?
I know they're building new stuff at the South Pole. Yeah, I can't remember straight offhand, but yes, there are much bigger experiments coming. Yes, the Xenon experiment, which is not up here, I know that they're building an upgrade to that. There's a controversial experiment which is looking at this wind of dark matter particles, which is in Italy, called the DAMA experiment. People are trying to replicate that experiment going forward, so build bigger ones of that. The problem with the DAMA experiment is that they have been reluctant to collaborate and share their scientific information. They have actually patented their detectors so people can't replicate it. So, because, I mean, this is a huge detection, right? I mean, and the stakes are very high. Whoever does it first is guaranteed a Nobel Prize. So people are, that's part of the problem at the moment. People realize that we're very close to detecting it, and then collaboration goes out the window. Okay, I'm going to end there.